Hello, morning everybody. Welcome to our event on AI in geospatial data capture, which is organized or hosted by the Geo Forum and National Land Survey Finland. So the Geo Forum is an organization whose goal is to promote the use of geospatial data for good, so for the public good. And we will have the privilege to have three amazing presentations today of what can be done by applying artificial intelligence, in particular machine learning techniques, to geospatial data. So before we start with the first presentation, just to give a quick overview or a quick introduction to machine learning and geospatial data. So this brings me also to introducing myself. I'm Alex Jung. I'm an assistant professor for machine learning at Aalto University, where I lead the research group Machine Learning for Big Data and teach some of the main courses on machine learning at Aalto. So I typically start any of my lectures with what are the three main components of machine learning. And since it's early day and we are not in a lecture, so I will give the answer and I will only mention the main component of machine learning. So the main component of machine learning, in my opinion, is data. And then the question is, of course, what is data? So in the most general sense, data is nothing but a collection of data points. And here already in this terminology or in this name, data points, you see that the field of machine learning is intimately related to geography or the geosciences, because the name point appears already in data point. So a data point is, in a sense, just an upgraded version of the notion of a point that we use in geography or in geometry. So what is a point? It's just an object that carries information. And I guess many of you know that in geography already a point is just an abstract mathematical concept. So it's like a fantasy. What is a point? So I could say a point is the location of my fingertip here, of my left fingertip. And then I can say, what are the properties of this point? Is this something that is fixed in space, or is this something that is varying, moving around in space? So is the point, the data point, something fixed in the space, or is it, for example, my finger that moves around and has properties like it belongs to Alex Jung? So, and you will need to point could be a certain location on the surface of the Earth that has coordinates as its features. However, it could also be the object that is located at a certain point in space. So a data point could be a stream or a ditch. So one key challenge here is to map out all the ditches and streams there are in Finland, and there are many. And we could say a data point is not a specific location near a ditch, but it's the ditch itself. So the data point is the ditch. Another presentation will talk about Finnish heritage, cultural heritage. So a data point where near, let's say, Turku, but the data point would be like a prehistoric there's already a lot of modeling coming into play when you have to define data points. And often these data points are related to locations. So, and whenever you can relate a data point really to a point in the more original sense of a location somewhere in space, then we call it geospatial data. Three particular applications of machine learning to such geospatial data, which uses data points in some sense that come with a location tag. And the first provided by Lingli Zhu of Finland, and she will talk
Good morning, everybody. I'm very happy to present Autumn Project here because I think this is quite special for me. After Corona, since 2020, this is the first event actually I physically visit the place and give presentation. So now let's start presentation, and I introduce myself a little bit. I'm Ling Li Zhu, from a chief specialist from National Land Survey of Finland, and actually I'm leading Autumn project, which is we can also call it AI project. And my background is I received my master degree and the doctor degree in Ardor University in photogrammetry and the remote sensing field. And the Autumn project, let's start, go forward. Yeah. Sorry. Okay, yeah, okay, thanks. Yeah. So today I'm going to talk about the Autumn project, why and why we need this Autumn project, and what is Autumn project, and the plan of our project, and the status of the project. And finally, I will give a summary of the project, of today's talk, sorry. Sorry, next. Yes. Sorry, I have to. Okay. Okay. Thanks. Yeah. So now, so why did we need this project? And now I give this background information why we applied this project. First of all, in National Land Survey, we topographic map updating is very like annually. We have a lot of people working on that topic manually, which is very labor-intensive work. And also in National Land Survey since 2020, there is a new area image, which is collecting the area images covering the 1/3 of areas in Finland. And there are a lot of data coming in every year. And also new LiDAR data from 2020, which is covering 1/6 of area in Finland. And also in AI applications, there is a big trend in using the geospatial, using AI for geospatial application. Oh, sorry. I have to go back. Yeah. All right. So what is the AI project about? So this Autumn project is a 2-year project which started from the January of 2021 to the end of this year. The Autumn means advanced technology for topographic map updating. So in this project, we are started to use AI like deep learning techniques for national topographic map updating. And in this project, we are focusing on the buildings, roads, and hydrographic features updating. Yeah, so this is the project plan. We have 4 work package in this project plan. The first one is the collecting the training data sets of buildings, roads, and hydrographic features. And the second work package was about the deep learning method development for building, road detection, and also change recognition. And the third one was the deep learning method for hydrographic feature detection. And finally, the last part, we we are going to have the evaluate the result by the expert from National Land Survey of Finland. And during this project, we focus on the deep learning method development. For example, deep convolutional neural network, transfer learning technique, and the multitask learning technique. Okay, so now let's have a look what's going on, what has happened during this project. And at the moment, we have collected a lot of training data sets, or we have produced more than 90,000 square kilometers, true also photos and the DSMs, and more than 2,000 kilometers building labels, and also more than 1,000 square kilometers road training dataset, and plus 36 square kilometers training datasets for hydrographic features. So those training data we have, especially very high quality of the training data for our project. And from the figure, you can see usually in the machine learning or deep learning project, the getting training data took a lot of time, much more time than the data we are using in neural network or the development for the neural network. So we have achieved quite a lot in getting high quality training data during the year. And also in technical development, and we have developed uses deep learning convolutional neural network for buildings, and also transfer learning technology and multitask learning technology. And those has been developed and achieved quite good results. And also there are something still going on for the hydro features, and also change detection for buildings, and change detection for roads. Those are still going on. And here I'm want to especially thank for the CSC environment. I think we in this project we have used the CSC, this high performance computing environment, and we got great support from the CSC, and we thanks for that. Yeah, let's have a look what kind of training data sets we have. We have multi-sourced high-quality training data sets. From the images you can see, those are all training data that we have in our autumn project. We have the buildings with very detailed outlines, and also we have DSMs, and also we have LiDAR data and vectors, building vectors, and also road vectors, and the vectors from hydrographic features. So here, let's have a look overview of the method that we have used in this project. For building detection, we have explored several different type of the neural network, like UNet with transformers, and the UNet with transfer learning. And during this testing, and we noticed, we compared the UNet with the UNet and the transformers, and we noticed like our result from the UNet, it's comparable with the UNet with the transformers, because there's one reason, probably because UNet with the transformers is like for, especially for large amount of the training data sets, and the size of the training data affects the results. And why did we use the transformers? Because in transformers, it has been in recent years, it has been very popular in the machine learning, and lot of applications. People say it's some revolutionary in the machine learning. So that's the reason we also try to keep up the techniques in the machine learning to use the latest techniques. But in our case, after our study, and we still keep the unit without transformers. In our case, it's because we got a better result, and with the transformers we got good, like we noticed that there are some good results for the big buildings, but there are some like more false detection coming. So in that sense, I think we still remain our original method with the unit. And also why we started this transfer learning, because the transfer learning is good for one in the case we are lack of training data sets. For example, we have very unlimited amount of training data set. So if we use transfer learning, we can use the pre-trained model from the existing sources, for example, like open data source and so on. And then we can use those pre-trained model and plus the local data sets for training and to get the good results. And later on, I will show you because in more detail about this. And also in road detection, and we have developed the multitask learning techniques. And we studied about for the different type of the neural networks like UNet, DenseNet, UNet, and the roadback net, plus different colors with different color spaces like RGB, HSV, LAB, and YCBCR and YUV. So later on, also there are more examples we'll show here. And then hydrographic features we have studied using UNet and for ditches and the streams. And later on, there's one presentation will give by Christine, and he will introduce more in this topic. So this is the master thesis about the transfer learning for building detection. From our study, we noticed we studied different techniques in the transfer learning, and we noticed the size of the training data is a matter. If you have more training data set, you get better accuracy of the model, final model. So, and also with the same amount of the training data set, and if you use different techniques in the transfer learning, and you will achieve quite a different kind of result, the up to 5% of accuracy up if you choose the right one. So here is another case of our master thesis about multitask learning techniques for road detection. And we in this study, as I told, we have used a different network and also different type of color spaces data set, and we achieved quite a good result. And with multitask learning technology, the good thing is you can have a multi-input and also multi-output. It means like for the traditional unit, you can only like output like building polygons, for example, from the neural network. But with the multitask learning, you can export like output with both polygons and also vectors. So you don't need to have this kind of post-processing. So this is the advantages. Here, have a look at this multitask learning. We use the we tested with a different neural network and plus the like RGB. This is only one color space. So we tested and we noticed the roadback net achieved the best performance. And this is another example study we had, and we noticed like we use a different network and also different combination of the color spaces and achieved quite a big difference of result. For example, if you see this IOU, the difference can be from the lowest to the from the maximum and the minimum. You can see the difference can be more than 5%. So I think this is a good example, and to give people this kind of knowledge that when you process the data set and you have different options to use the different kind of to use the right combination of the color spaces and also the right selection of the neural network. So it's important. And for the buildings, we have tested data for Laajasalo, Helsinki area, for our National Land Survey expert evaluation. So this is the area, like we more than 3,000 buildings have been delivered to our expert last year, and for the evaluation. So here is the example of the predictor result and the vectorization. So the left one is the polygons from neural network, and the right one is the outline of the buildings. So you can see we can achieve the very high detailed building outlines from our neural network. So here is shows the result evaluated by our National Land Survey expert. So basically, here I only show the 2 cases, but actually our expert compared our Atom project result with the 5 different type of the data set. And for the evaluation of the buildings, we also got like a pixel-based result, like F1 score in neural network with 0.953 F1 score. And also for the object-based level by the National Land Survey expert. And I just, there are some Finnish sentence there I just directly copied from the report and then give and show here, but I can explain a little bit about this thing. Our Atom project was compared with the building RHR symbol database, and we got 97.9% of the building detected by our project. And also the second one was our result was compared with the topographic database building vectors. And then we got 93% of the buildings were correctly detected. And then I have checked what's the errors come from, and is there any possibility to improve the result. And from the report of the evaluation, and it touched some buildings with errors, and some buildings existing in the topographic database, but not detected in our project. And I noticed that there are many kind of cases which, like in forest, for example, like some even I may say even use human eyes from the image, it's very difficult to recognize it because it's under trees. So it's basically quite many cases like the buildings, it's not visible in the images. So in that case, I may say what we achieve at the moment, it's the best result what we can. Here is the overview of the result from our our project at the moment, and we have received quite a good result for building detection, and also we got good result from the road detection, and also quite a promising result from hydrographic features. So as a summary, so Autumn project is dealing with the topics of building detection, road detection, ditch and the stream detection and the change recognition of buildings and the roads using deep learning techniques. So far, we have achieved excellent results from building detection, and the results were evaluated by National Land Survey expert. 97.9% accuracy has been achieved. So there have been 2 master theses accomplished, and the 3rd master thesis is on the way. And there are some other plan is coming, and we will present in 4G 2022 conference, and our paper with the academic track has been accepted. And also for road detection result, and we'll go for expert evaluation in coming months. So that's all information from our autumn project. And thanks. Thank you for your attention. And if you have any questions, please leave it in the chat and I can answer later. Thank you.
Thanks a lot, Lingli, for this very interesting introduction to the ATMU project. We will now have the pleasure to hear more about this ATMU project by Christian Koski, who is also with the National Land Survey, and he will tell us about how to map small streams and ditches with deep learning.
Okay, so good morning from me too. So my name is Christian Koski, and I come from the Finnish Geospatial Research Institute in the National Land Survey of Finland. And I will give my presentation about mapping small streams and ditches with deep learning in the ATMU project. So let's see if I can change the slides. Okay, so in this ATMU hydrographic features part, the focus is really on small natural streams and ditches. Those are the most sort of the features with the most potential for improvement in the National Land Survey's topographic database. Traditionally, they have been quite difficult to map, but now with high resolution elevation models, they can be actually quite well detected visually. And yeah, there's a lot of potential for improvement. And now also, as other features are being extracted from the elevation models, such as contour lines, there's some inconsistencies with the automatically extracted contour lines and the current natural streams and ditches, or small natural streams and ditches in the topographic database, and we are hoping that this will also be fixed then. And really, we are focusing on these less than 5 meter wide watercourses. So, if I can change the slide again. Okay, so okay, now I lost the slide here. Some technical difficulties. Let's wait. Okay, so here's the overview of the work. So I've divided this into sort of 5 parts. So we have the training data, then we have the input data, then we have the deep learning framework, the post-processing, and then we also want to do some assessment of results. And currently, we are at the phase where we sort of have the first iteration of this training data, input data, deep learning framework, and post-processing. But we are starting to now improve all these different parts. So I will next go into all of these in a little bit more detail. Can I change the slide, please? Okay, so first I will talk about the training data. So we have digitized manually all watercourses from an area of 36 square kilometers. and we have used a variety of background layers for this. So from the elevation models itself, you don't see those ditches and streams that well. So we have used mainly a topographic position index to visually highlight these features in the terrain. So the topographic position index, if you are not familiar with it, it's the difference between a point's elevation and the mean elevation of its neighborhood with a given radius. And then we have also supported that with the use of hill shading layer. And then in a second iteration of trying to improve this data, we have also used flow accumulation layer to try to better detect natural streams. And then we have given these digitized features a type attribute, which can be basically a ditch or a, any ditch except roadside ditches. And then we have roadside ditches, and then we have natural streams. And the reason we want to possibly separate ditches and roadside ditches is because, for example, in the current topographic maps, we don't want to have roadside ditches. So this gives us a possibility to later possibly try to filter out some features and see how that works. And we have some preliminary experiments done on that as well. Then we have an uncertainty attribute, which gives a rough idea of about how much uncertainty is involved when digitizing that feature. Okay, we could change the slide, please. So about this uncertainty. So what to digitize? It's not so clear always. There's a lot of uncertainty. So for example, in this image here on the right side, there's this topographic position index, and it's quite difficult to tell exactly what is a ditch there and what is not, or what should be digitized from it. There's varying shapes and forms of features. There's partly filled up ditches. Some ditches are maintained, some are not. There can be growth in ditches, or there can be small bridges over ditches that then affect the elevation model. And then also the point cloud is not exactly perfect. There's some areas where there's not that many points in the point cloud, and then that makes it difficult to detect ditches under it. So there's a lot of human interpretation coming into play, and well, we have this uncertainty score, and we have also just used one person to digitize this whole area, and then we have a couple of other people who have just checked the most difficult areas there, and then decided together what to digitize. So once we have digitized these features, then we have made that into a label dataset by buffering the features 1.5 meter, and then rasterizing that into a 0.5 meter grid. And then we have made as input data, we have made an elevation model for the same grid, using a 5 point per square meter point cloud. And then during training from these data sets, we cut tiles from random locations, and then we do also some augmentations, random rotation, and mirroring, which is a 50% chance of it being mirrored. So these data sets are divided into 80% training data and 20% validation data. And of course, in validation, when we do the validation, we go systematically through the validation area. So we don't do any random things there. So we are using unit basically, but there's some modifications. So we have optimized speed here, and we have simplified unit a little bit. So this is the general architecture. We are planning to try some other alternatives as well, probably, or some at least other versions of unit during this project. That's a plan. And here is we get the results then from the unit. So we get an F1 score of 0.875. That is sensitive to where we choose the validation area from. So currently 36 square kilometers is not that big of an area, I think. And if we change the validation area to something else, we might get a little bit different score. But in terms of testing different things, trying out different things, we can use this as a reference. So here you can see then visually we have the label data set on the left side, and then we have the results on the right side. And well, if you look at it quickly, it looks quite similar, but there's some differences. So we can go to the next slide. I've highlighted a few of them. You can probably find more of them. So, for example, up in the left corner, you can see some additional ditches being found, or maybe they're streams. I think they're ditches. And then in these three other highlighted parts, you can see some sections of ditches missing. But this is a particularly good area, which is nice to show as an example. We can go to the next slide, where we have a lot more problems here. But I took the TPI here as well, the TPI layer, and if you look at it and compare it to where the problems really are, it's usually that the ditches aren't actually that clear in the TPI either. So those are quite difficult locations typically. But then we have also other kinds of tricky parts. One particular one is the natural streams. I think that's the biggest sort of challenge we have at the moment. That natural streams, we don't get those well mapped here. Usually they get cut like this. The green one is the label data set, and then the red one is the predictions. Roadside ditches, sometimes they cause some problems. It's sort of also, we don't know why. In this particular example, you can see under the green one, but they are actually quite clear in the TPI. And then we have this kind of wide watercourse sections which cause problems. It might be that they're not that common, so it can be a difficult kind of feature to detect. But they are problematic if we want to have the sort of water flow network, and the ditch gets cut there. And then this thing that I already touched upon is when you have quite sparsely these ground points in the point cloud, and you get sort of holes in the point cloud, and then the elevation model itself is distorted. So these are the most common kind of other problems, in addition to where just the ditches aren't that clear. You can go to the next slide. So in terms of post-processing, we have done this kind of vectorization process where we just polygonize the results, and then we do some simplification, because that helps in the next part, which is where we extract the center line with this kind of approximate medial axis, and then we just filter the shortest vectors out. But this is a very rough version, so this is probably going to be a little bit improved, but it works quite okay already. In Atmo project, we probably won't be able to do, however, all post-processing that is needed to get feature for the National Land Survey's topographic database, because there are far bigger issues. And one thing is that we probably don't want everything that we find in the final data set, and we might want to have some kind of classification there in place. So we might want, for some use cases, you might want the roadside ditches for maps, for example. You don't want the roadside ditches, so you need this kind of classification as well in place. Then there are features that sort of cut the watercourses, like pools and ponds. The water flows through, but they don't. They are not found with the unit network or with the model. And these pools and ponds, we have actually started to digitize them, and we might try to see how they could be found with machine learning. But then there are also even trickier features, like in the lower right corner, you see this image. There's sort of a swamp area, which is kind of narrow and long. And in the current topographic database, there's a watercourse running through that. and you can't really see it at all in the topographic position index. And really, it's not that clear which swamp areas the water flows through and which are just basically swamps with water staying still. Then we also have underground watercourses, and also that includes culverts, so where the water flows under a road, and those can't be detected with this method. And somehow, if we want to have a hydrographic flow network, so we want to know where the water flows, we need all these parts of the network in place. And that's something that is what the National Land Survey's topographic database features should be like. Okay, so in the ATMO project, what we are planning to do, however, is we want to test different input data. So we have only used the elevation model, but we could use something like flow accumulation, where something many kilometers away could affect something in another area. We could use the topographic position index itself, and then there's a lot of other layers also we could use, and we could use these individually, or we could use them in combination with each other. Then we also want to test different networks, like I already touched upon, and there's some networks that have already been used for similar use cases that we are particularly interested in. And then we want to do some kind of assessment of results, but it's not yet quite clear how we want to assess these end results, because like I said, we can't get the final features because of various issues that will probably not be solved in the ATMO project. So thank you. That was all from me, and you can probably place the questions in chat.
Christian. So our next speaker will be Nikko Antiraiko from the Finnish Heritage Agency, and he will tell us about mapping archaeological heritage with AI and LiDAR. So I'm looking very much forward to your talk.
Okay, thanks. Everything seems to be working. So, hello. I'm Nikko Antiraiko from Finnish Heritage Agency that you might know by the name of Museovirasto. It's normally called. And I'm here to talk to you about our project, LIDAR, that stands for something like mapping archaeological heritage with AI and LIDAR data. And to present myself, my background is solidly in archaeology, so I'm not a machine learning guy in that sense. And I am the project manager in this project, so I'm trying to run things behind the scenes so that everything works. And it works. And to present this project or the outline of this project, our goal is primarily to develop methods for automatic detection of archaeological sites of different kinds using artificial intelligence and LIDAR 5 points data from the National Land Survey. And our project organization is as follows. So we have two main partners in this project. It's the Finnish Heritage Agency and then the University of Oulu. And both of us have primarily archaeologists working on the project. And then we have a variety of different partners with different roles in the project. So we have Blomkartta as our technical consultant that actually has been responsible for our method development. And then National Land Survey, they, of course, are the producer of much of the LIDAR data, and also the topographic database is one of the most important databases we use. Then we have Metsähallitus They also have a huge interest in archaeological heritage in forested areas, and they have their own databases with lots of archaeological features. And then we have something called regional responsibility museums that are kind of the regional front line of archaeological heritage management that actually have to deal with the sites in real life. So they kind of do much of the footwork. And the funding for the project comes from the Minister of Agriculture and Forestry. So this is one of the kind of LIDAR 5P pilot projects they decided to fund. And I guess there are 3 other similar projects. And to continue, I could maybe talk a little about our use case. So currently, there are about 68,000 known archaeological sites or features in our databases. And these include a wide variety of different things. Some might be protected by the law on archaeological heritage, and some are just some other culturally important objects we might be interested in or like to protect. And these sites are likely just the tip of the iceberg, really. So we estimate that there are more than 500,000 such sites in Finland. So most of those remain to be found. And the motivation for this is, of course, that the sites we don't know about, we can't protect or study in any way. And those are constantly at risk to get damaged by like forestry practices or land use, basically. And also, this kind of exposes the fact that the databases we currently have are not that accurate in spatial terms. So the spatial information is usually imprecise or in some cases just plain wrong. So we like to correct that if possible. And what's nice about the archaeological features is that many of those are easily detected in LIDAR data and have like visible features. And that makes it like a huge opportunity to apply AI or machine learning based methods to actually map those. And the picture on the right shows a really good example. These are tar kilns and charcoal kiln that are really nicely visible and have been mapped by our AI systems. Yes, and of course, not all of our archaeological features are suited for these kinds of studies. So we are only limited to those that exist in sufficiently large numbers, like thousands of sites, and those that are actually identifiable in really clear terms in LIDAR data. And to just show a couple of examples, the picture on top that might be a bit small, it shows a chain of hunting pits that are quite common in northern Finland. And those are one of the sites we've been studying in this project. Then the picture in the middle shows field fortifications from Eastern Finland from World War I era. We have a huge amount of those as well. And then the picture at the bottom shows some Bronze Age burial cairns that might be a little bit more difficult to see, but also interesting. So we are looking at these kinds of features and of course the tar kilns from previous slide. And the methods we use are actually pretty similar to some of the previous presentations. So we use a UNet-based image segmentation model. And of course, like the reason we are using this kind of method is that we are interested in like the areas that contain the sites. So we chose to use a image segmentation approach instead of like traditional object detection that might just detect the sites but not like outline the precise area. And also one of the like good things is that this model tends to perform pretty nicely on relatively small training data sets. And that's one of the problems we are kind of dealing with. There aren't that many known archaeological sites of given type. So we have to like make use of what we actually have. And our workflow looks something like this. So for LiDAR pre-processing, we use the same kind of topographic position index as Christian. The difference is that we use slightly smaller cell size, so we are actually upscaling or upsampling the LiDAR data to a higher extent. So we use 25 centimeters square size. We also made some tests with like Corsair model topographic position indexes, and we kind of lost around 10% of the detected features if we used 0.5 meter square size. Then we also do some other visualizations, mostly for visual use. So archaeologists have been using LiDAR for a long time, so most of us already have our favorite visualization we like to use for actually digitizing our training datasets. And for creating our training datasets, we have collected data from various registers and databases from Heritage Agency, Land Survey, and Metsähallitus. And then we have combined the features from those databases and digitized everything in there, and also digitized some new features, as usually there isn't quite enough features from the databases that exist. Then this machine learning part is fairly standard. I'll just move to verification. So we have done some automatic post-processing for the data by using a Python script that groups the detected features in like aggregate groups if they're really close to each other. That makes verification a bit faster. Then we calculate some attributes to help with the verification, like roundness, size, and so on. And we do most of the verification work just by looking at the data in GIS. And of course, if the cases are a bit unclear, we do also some field work. That's really limited. And after we are satisfied with the data we've produced, we process it for other uses, such as reusing it as part of another training dataset, like adding it to the existing databases or research uses. And these all kind of require a bit different modifications to the data, and also might like need different levels of certainty that the features in the data are actually correct. And just to present our first case study in the project that acted as like pilot study inside a pilot study that was aimed at like getting our methods to work and like prove that the whole concept is viable. And we chose one research area in Kainuu, mostly based on that we knew that there are a lot of tar kilns that are one of the easiest archaeological objects there is to find and identifying LiDAR data. So we tried to make as simple use case as possible in this point. And we did this a couple of times over, improving our methods and training datasets as we progressed. And at around third iteration, we had something we were quite satisfied in. And just to show how this affected the situation of known sites and so on. So before our study, we knew around 800 tar kilns in the research area, and this number increased more than threefold after our project. And this is, I must note, an area where we actually knew really many tar kilns to begin with. So this is kind of the best case scenario for the existing databases. And what we were particularly impressed was that very few tar kilns that could be identified were actually missed. So currently we know of less than 50 cases where there probably is a tar kiln, but our model couldn't identify it. And to show something about the precision of the identifications and the limits of the sites are identified by the model. We have an example of like polygon from our training dataset on top left, and then some examples in red in other pictures that are polygons produced by our model, and these are pretty much spot on. And also, what's kind of evident in these pictures is that the model is also pretty good in finding damaged or partially destroyed features, like features that have been plowed over in forestry practices or so on. And that's something that's really important for us. The amount of false positives, of course, we have quite a lot, but that turned out to be manageable so that we can actually verify all the results by hand after this. And there's also actually an example of one of the false positives in the lower right corner. So the model seems to like ditches also and identifies those quite often as tar kilns. And after this like initial pilot study, we've been trying to scale up the project. So we've applied the same to around 20 LiDAR 5 points production areas, and also some other types of archaeological features. So tar kilns and charcoal kilns were the two first ones, and probably the most simple. Pitfall trap systems, and then, of course, the World War era fortification systems. And also we are trying to add more types of sites as we go on, like Stone Age dwelling depressions that, just to tell you a little about what they are kind of remains of semi-subterranean dwellings from Stone Age. So that's something that we archaeologists are really interested in, and it would be really cool to actually venture into older and maybe more interesting features as we progress. And just to summarize some of the results so far, so we have been able to identify over 10,000 previously unknown cultural heritage sites so far, and this number is still increasing quite rapidly. And yeah, so far most of this increase comes from tar kilns, charcoal kilns, and so on. But we expect that we probably will find also thousands of like pitfall traps and fortification objects from World War I and II. And as we progress with more like identifiable features, the project also becomes slightly more challenging. So we already kind of exhausted the simplest and most easily identifiable features. And for example, like the Stone Age dwelling depressions I was speaking about you earlier, this picture here shows one example of such sites. You can't probably see my cursor, but there's like these small depressions visible in the hillshade that are quite easy to mix with natural depressions, and that makes detecting them with AI much more difficult than with the more clearly identifiable features. So this is something that we kind of consider possible, and we had some limited success, but this is probably something that we must be like prepared to accept, that the performance of the model will not be quite as high as with the more easily identifiable features, and the results will need much more verification in field. And to conclude, we've been really impressed with applying artificial intelligence to mapping archaeological features. We have produced unprecedented amount of data in this field. So after the project, I expect that 1 in 4 known archaeological features is something that we've identified in this project, which is quite impressive considering that we've been doing this for 150 years in this country. Also, the quality of the spatial data we produce is much better than has been previously possible, and this is going to change a lot of things in cultural heritage management field. And also, it's become evident that this amount of data we produce produces some challenges for the whole cultural heritage management sector in the future. One is that, of course, there is a huge amount of data, and some of the existing processes for protecting these sites are just not efficient enough at the moment. So we have to come up with new ideas how to actually manage and protect those sites. Also, we don't really have any guidelines for using the data produced by such methods. So we have to make sure that we actually start planning ahead and making sure that the guidelines are in place when this becomes even bigger than it already is. And also the current legislation that governs the cultural heritage management is quite old, and some changes might be in order to actually accommodate these kinds of methods in the future. And this process is also ongoing. I'm not quite sure what the results will be, but I hope they are for the better. And that was what I had to say. Thank you very much.
Thanks a lot, Nico, for this very exciting application of machine learning techniques. So now, after we had this pleasure of the three talks about the state of the art in geospatial machine learning, we will have the possibility to discuss your questions and our questions within each other within a panel discussion. So we will now kick off the panel discussion. Yeah, do we have any questions yet from the audience? No. Okay, then I might take it away. So my first question would be, what is the most impressive achievement of a particular machine learning technique that you have observed? So we have heard about transfer learning, we have learned about data augmentation, we have learned about multitask learning. Did any one of these individual techniques really make a difference? Maybe let's start with Lingli.
Yeah, thanks. Thanks for the question. And also I want to thank you, this Job Forum, for this opportunity to have me be here. So it's very nice to be here. So for the achievement, I may say during our autumn project, we have achieved quite a good result from, like, first of all, we explored the different type of the method in deep learning, and we started from the zero, and now we are dive in this deep learning, in this AI development. So we know more during our project, and also about may say the achievement so far. I think the best thing is that we got very good result for building detection, and also we have had this evaluation from our expert. I think this is a very big result. I mean, not only for like a research point of view, like for publication or write papers, but we put those methods, it's ready to be used in practice, because we result has been evaluated by our experts. So it's a big step forward, I may say. When I had some conference or workshop with the other countries, and they admired about what we have achieved. So I'm appreciate about this the people work in this project, and also I'm proud of the achievement what we have so far.
Thanks a lot, Lingli. So maybe Christian, as you also engaged in this ATMU project, I remember hearing about data augmentation you have used.
Yeah, actually, that's one thing that really did improve. Also, the fact that we use the whole data set and then we take from a random location the tiles that helps fight the overfitting problem. Because we have quite a small amount of data, you could say.
Yeah.
Because it's so laborious to digitize, and we don't have the possibilities in this project to really do huge areas.
Yeah.
So those did really improve the results quite a bit.
There, I was wondering, did you also take into account some physical knowledge for data augmentation? Like I've seen you have used random rotations of tiles, but for example, that what I had in mind, but which might be difficult to implement, like knowledge that a water typically doesn't flow in closed cycles. So water runs from higher place to lower places.
I think that's the case for natural streams, yes.
Yes.
But then you have ditches, and
Yes.
actually you might have like a ditch somewhere in the middle.
Yeah.
Nothing where.
Because one very useful property of data augmentation techniques, as I see it, it's very convenient to bring in domain knowledge, like experts. So, because how would you bring in like a hydrographic model or fluid dynamics? And one way to bring it in is to use this physical theories or physical knowledge to simulate data. So that's why I was thinking of bringing in this background knowledge or domain knowledge using this data augmentation.
Yeah, that's an interesting idea, and we have actually started to talk a little bit more with people with domain expertise, and sort of the point of the first iteration here has been only to see, well, what can you get with this kind of simple solution.
Yeah. So you have some pretty good ideas how to go further.
We have some ideas how to go further, and we'll see where we get.
Very good, very good. Okay, then Nico. So, what particular technique, machine learning, off-the-shelf technique, did you find impressive, or where you could see a clear benefit?
We were mostly focused on UNet, and we've been really impressed with that. We've kind of been looking for other options as well to like compare and see if we might benefit from like implementing some other models. But so far, actually, the results from UNet have been so impressive in their own right that we haven't really like put much effort in changing our methods. Of course, one of the things in our project is that we've been trying to keep everything as simple and streamlined as possible, as we are kind of doing this with relatively limited resources, and that's been really useful for that kind of scenario.
Yeah, may I ask, did you have in your team some data scientists by training, like some people who studied machine learning at university level?
Kind of no. That kind of expertise was brought by a private company to our project. So our like model was to like buy the kind of method development from outside, and then we had one archaeologist with some kind of coding experience. That was me. So my challenge was to kind of jump into a moving train and just.
Yeah, as I see, one of the big drivers for the success and the hype of deep learning or machine learning in AI is this increased usability or ease of use of technique. Because you don't need to study applied statistics for 5 years at the university anymore. You can buy it as a product. So you can buy as a product image segmentation using UNets.
Yeah, absolutely. And if you kind of know what you want to have, you can kind of buy like a product that's tailored to your needs pretty much.
Yes.
It isn't necessarily even terribly expensive, so it's quite easily available to pretty much everyone.
Yes, yes. Thanks a lot. So I see we have a question for Nico. So the question is about other heritage agencies. Do you have collaborations with agencies in Sweden or Norway, or do you know to what extent they use AI and LiDAR?
Yes, there are quite a few other agencies doing something similar. So, for example, in Norway and Sweden, they are doing something similar. In Norway, they have been doing this for a couple of years now, and I think they're pretty advanced at the moment. They use slightly different methods, so they're really interesting point of comparison to ourselves. The Swedes have just begun. They have, I think, at least 3 different projects that they are trying to combine later. And also in continental Europe, for example, in the Netherlands, they have really advanced project. They're using like multi-class detection models and so on. Yeah, there are plenty of similar projects and things going on around the world at the moment.
Yeah, and this example also shows that one of the key benefits or abilities of machine learning, this transferring of knowledge or transfer learning. So if you're able to detect this, as I understood, kiln sites, charcoal,
Yeah.
kilns, if I remember correctly, this seems to have been very important for people earlier for a good reason. So if you know how to do it in Finland, you might be able to use that knowledge to do it also in Sweden or Norway, and maybe use, that's what I also would like to add the question, do you take into account also, as in the other applications, domain expertise, like people or scientists who study the behavior of people, like anthropologists? So they could tell you if there is this kind of site, like a kiln, then there should be within 100 meters, there should be dwellings.
Let's say, yeah, to answer the first part, some of the training data is usable pretty much over the world. For example, the tar kilns and charcoal kilns are pretty standard features that are built using the same manual books. Really, so they are the same, and we can share that kind of data with pretty much everyone, and it's usable as it is. And the second part, we are that kind of experts ourselves, so that's kind of our point of departure. So we have this kind of archaeological knowledge what should be nearby. So yeah.
And just to go a bit more technical, how do you bring this in? For example, I mentioned before, data augmentation would be one such opportunity. So if you have an image where you know there's a certain dwelling, then you could create a synthetic new image that you would hypothesize another dwelling that could look similar, but maybe a bit rotated, slightly different.
Yeah, we've been doing data augmentation.
Yeah,
that's, of course, we are working with pretty limited data sets, especially with like the dwelling depressions. So we're doing the same rotate, mirror, like flip axis kind of things. Also, we usually take like 2 random snapshots of each object in our training data set to create randomly centered versions of the same images.
And do you use, but for this, this seems to be very, so we have an echo here, sorry for the irritation. This seems to be a standard or rather agnostic ways to augment data. So this, one of the cat images. So a rotated cat image is still a cat image, but when you talk about dwellings or archaeological sites, you might have additional knowledge, like you need to have a certain configuration of buildings in a house. So you could generate new images by using a different variation of a typical old Finnish village, so to say.
Yeah, that's an interesting proposition. We haven't really thought that. We've mostly considered using that kind of information for filtering the data that's produced. So that if we kind of know that, for example, Stone Age sites are in a given area, they must be at least 20 meters above the sea level, and not much higher than some certain height. So that helps in limiting the amount of data we have to go through and verify.
Yes. Yeah. As I mentioned, I think this could be a convenient way to bring in domain knowledge, like from anthropologists in the data augmentation, because this just means you have to enrich your data set by new synthetic data points, whereas other ways to bring in domain knowledge could be to think about specifying a new model architecture, like changing the unit. which might be considerably more difficult, for which, or for such an approach, you might need to have a university degree in machine learning, maybe. But in this data augmentation, I think this is really one of the most convenient way to bring in this domain knowledge. Okay, yeah, that was a great first round. So I would like then to kick off the second round of questions, which is, of course, after the praising of machine learning, what was a main challenge in your specific field where maybe the promise that you expected or that you heard about machine learning didn't really materialize yet? So what is a main challenge? Maybe again with Lindley.
Thanks for the question. I think at the moment the most challenge is about because for the traditional neural network we only input data like the certain, for example, images, and but in our geospatial field we have the LiDAR data, point cloud, which is the 3D, and the images usually it's 2D, and how to like combine those data set and to use at the same time to be beneficial for the final detection. So that's kind of a challenge, because at the moment for the LiDAR data we have the X, Y, Z and also intensity value. So when you nowadays when people how do they use together with images, they use like X, Y and Z, or X, Y and intensity value. So that means something missing from the LiDAR data when you are using together with images, because you transfer the LiDAR data 3D data set to the 2D, something might missing. So and another thing is like somebody do individually only use the LiDAR data for the classification, or only use the image for classification. But our challenge, I think, in the future might be like how to use them together in the neural network. So that will.
I hear that data is a main challenge, and I remember also from your slides where you showed the time allocation. So most of the time goes into gathering training data.
Yeah. I think because actually in National Land Survey we have a lot of countrywide open data set, like a topographic database, which has a lot of building vectors and the roads and such. But why cannot we use those? Because the building vectors from National Land Survey topographic database was from the footprint, the bottom of the buildings. But from images, when we use the machine to detect, so it's from top of the buildings. So there are some kind of different, like when we teach the machine how to detect the features from images, we have to have kind of like outline you fit for the images. Mm-hmm. So we cannot use the original kind of building vectors from the open data source. Mm-hmm. So this is a very challenging, but luckily we had some trainees and we had several people like helping, mm-hmm. Especially for this manually, like for high quality training data collection.
Yeah.
So it helped a lot, and finally we got the result. It's, I think, beneficial from the high quality training data.
Yes. Yes, yeah. And there was a reason why I mentioned that data is the main component in the beginning of the event, because I see also this as the most challenging part. And maybe Christian, also you can confirm that the most work goes into data.
Yes, that's by far the most difficult part. Like especially for us, where you have ditches and streams, and they can be quite different from each other, and they're not that clear even in the terrain. If you go there and look at them, you're not always sure, is this a stream?
Yeah. Okay, so you also confirm, and I guess also you, Nico, the most challenging part is the data part for machine learning and AI.
Yeah, there are like two challenging parts. One is of course the data. We have exactly the same problems that like gathering the training data is not that simple, as like the objects you are trying to collect are not always that similar and might be really difficult to like detect or like to conclude that, okay, is this something I want to have in my training data or not? And the other challenge is something that comes after the machine learning phase is actually making use of the huge amounts of data it produces. That's actually one of the main challenges for us, as we are trying to bring unprecedented amount of data to an already existing process, and it's proving quite challenging in many ways. So.
Yeah, that's actually a good point. I heard a long time ago when I started project management during my studies, we heard that there's this new paradigm. When you plan to build something like a train, you make a full life cycle. So you not only plan how to build the train, but also you will recycle it afterwards. And I was wondering, do you have already such initiatives regarding the data usage? So at some point you cannot store the data anymore, because I guess the memory your institute has available is also finite, the storage capacity. So do you have already a plan when and which data to erase?
Kind of, we do, and well, we've been starting from the other end, which parts of the data we want to actually keep and for what kind of uses. So we've kind of made a plan of which kinds of data we can publish, and maybe have it in some kind of place that kind of keeps it long term and available to everyone. And then, of course, part of the data must be added to our registers and databases that we use daily, and that's kind of the other part. And then all the rest we are kind of prepared to ditch. It's we're built our system so that all the rest is kind of replaceable quite easily. So we are kind of concentrating on the most valuable parts.
Yeah, and I guess it's quite challenging to find out the most valuable parts. And also, it might be not a 0-1 decision, so either delete or keep it, but you might only keep a more coarse version of data, like data aging techniques. Yeah, and I was wondering, is it the National Land Survey? Do you have these long-term plans for how long to keep data, when to erase data, or which parts of data to keep? If I might ask Ningli again.
In National Land Survey, we have this topographic database, which is open to the society, so everybody. And annually, we had this data updating, like map updating. So we keep up the latest version of the objects and the changes, and we manage it like that. So it's a stay all the time. You can download when you need, and so there is no kind of time limitation when it will be there, but it will always be there.
Okay.
So you can use any time when you need, you just download from the website. So just search open data from National Land Survey of Finland, so you will find the link, and very handy.
Yes. Okay. Then, maybe the last round of question. I would be interested in maybe one of the most difficult aspects of using machine learning, to know when to stop. So when you know you cannot go any better. So this UNet architecture with this number of layers is optimal, or there might be still some benefit to reap. So do you have such ultimate gold standards for accuracy in detecting buildings? Or is this, and in many cases, you don't have such a benchmark. You don't know, principle, if you can do better or no. You can only find out if you try out a new method.
Yeah, I think in our case we tested with the different kind of, not only UNet but with the others.
Yeah.
But then we compare what's the performance from the different your network, and also with the UNet we had quite the deep kind of experiments. For example, first of all, we only use the images in the UNet, and then we noticed we can use the different, for example, color spaces. That's the one thing. We can add one more channel in the input data, and also later on we also put the DEM and the DSM in more channel in the input data, so to improve the result. Yeah. So we go in that way, in wide way we tested it with a different type of the neural network, we also go the deeper way, like with the unit, and to get improve the result with the one certain of the network.
Thanks a lot. Christian, do you have a gold standard for detecting ditches and streams?
Not in terms of like a threshold value we would like to get to, but mainly I think if we look at the errors that makes the network makes, then if we can explain those, and we know that we can't improve that with another model. Like if the problem is in the input data or in the training data itself, then that's fine. But we still have maybe a few areas where we could improve with trying out different models, and then it's just how much time do we have in this project and resources, where the time sort of stops that okay. So there's two possibilities. We don't have enough time, or then we can explain all the issues that it finds, and then it's fine.
And would you say that the deep learning methods that you're using, they're already outperforming gurus that look at an aerial photo and see there's ditch, the stream here and there? Is it already on par, at least, with humans?
I would say it's sort of similar. Well, I would say people still outperform the machine learning because especially when you have some kind of issues in the point cloud or these issues that we have, streams, especially natural streams, we can see quite well where it actually goes, but the machine learning algorithm doesn't really still find those.
Yeah.
So at the moment, I would say still the human outperforms the machine, but it's actually, we are quite impressed with how well the unit also performs.
Thanks. Then Nico, what is the benchmark in your case? I mean, it might be hard to be sure. We now find all cultural heritage sites because humans might have been in every square meter around Finland at some point of time.
Yeah, it kind of depends on the application currently at hand. So we have like different requirements for like detecting really numerous sites like Tarkins. Then we would like to have as little false positives and that kind of problems as possible. But if we're trying to find something else like the dwelling depressions, I've been talking a lot, then we might be prepared to accept much limited performance as long as it finds something that's potentially an archaeological site, and spend much more time in actually looking at the results, and it would be a huge thing to find even like a dozen new sites in that kind of scenario. So it really depends on the case, what we are prepared to accept.
By the way, is there a legal ground or framework who defines what cultural heritage site? Yeah, I guess it's by definition this cultural heritage site, like the UNESCO on a
no. There is a Finnish law on archaeological cultural heritage. Kind of defines what's protected by that law. Of course, it doesn't cover all kinds of cultural heritage objects. So then there's a huge amount of stuff that isn't covered by the law, but we kind of would like to protect and use. There are different instruments for defining those. It gets a bit messy.
And is this law, just to give an idea, is this like if at this site there have been baked tiles and there have been baked bread, then this is a cultural heritage site?
Well, it could be. There is kind of a time limit for defining what's covered by the law on archaeological cultural heritage, and then all the other cases are like case-by-case decisions, basically.
Very interesting. Okay, thanks a lot. I guess we are out of time. It was a great event. I really enjoyed also the panel discussion, and I look forward to some follow-up events. Thank you.